Hello, this is True Socrates. Welcome to a portrait of linear algebra. Now, in our last video, we were introduced to operations on linear transformations and matrices. So this video will be essentially a continuation of that video. So obviously, if you haven't seen it yet, it would be a good idea to see it first. So as the title implies, we are going to learn that the matrix operations that we just saw possess many properties which are very similar to those found for vectors and of course for real numbers. But there are some notable exceptions. So we will warn you not to do certain operations in certain ways which are not substantiated by these properties. We will find how to compute the power, any power of a square matrix, starting with a square. You can make also a cube, the fourth power. And from these, we will show you how to evaluate a polynomial at a matrix. So let's start with the simple properties, which relate to matrix addition by itself, or scalar multiple by itself, or a combination of the two. So we have three matrices. They're all m by n, all the same size. And you have two scalars, r and s. Then we have these five properties. We have a commutative property for addition. A plus b is the same as b plus a. Associative property for addition. If you have these three matrices, you can have a plus quantity b plus c on one side, and a plus b together added to c on the other side. You should get exactly the same final answer. You have these two scalars, r and s. You can add them together and then multiply by a, or you can multiply a individually by these two scalars and then add those together. You should get exactly the same answer. Now, you can also take two matrices, a and b, add them together, then multiply by scalar, or you can multiply those two matrices by the same scalar and then add them together. You should get exactly the same answer. Now, you also can multiply by the two scalars. You can multiply a first by s and then multiply that answer by r, or you can multiply r and s together and then multiply that answer by a. Or you can multiply a by r and then multiply that answer by s. All of those will give you the same matrix. And of course, we saw properties like these all the way back to real numbers, and of course also to vectors. So we keep the same names for these properties, even though they're applying to different objects, matrices this time. They're all easy to prove. And essentially, all you have to do is look at what is found in row I and column j of each side of these equations. Let's take the first property. Why is a plus b exactly the same as b plus a? Well, in a plus b, who will you find in row I, column j? So in the last video, we said, oh, just look at the entry in row I, column j of a, and also of b, exactly the same entry, and add them together. But now, they're both just numbers, so it doesn't matter which order you add two numbers. We have a commutative property for real numbers. So the sum of these two numbers is exactly the same if you reverse the order. If you add the entry in row I, column j of b to the entry in row I, column j of a, then you should get exactly the same answer. But again, by definition, this sum is what is found in row I, column j of the matrix b plus a. So a plus b, the entry in row I, column j, is exactly the same as b plus a, the entry in row I, column j. So the two matrices are exactly the same. Okay, now it gets a little bit tricky. We will see properties of matrix addition when incorporated with matrix multiplication. So this time, we have two matrices A and B, which are the same size, m by k, and then we have two matrices C and D, which are a different size. They're k by n. And we have a scalar r, like before. We have a left distributive property. We can add A plus B together first, and that will produce another m by k matrix, and then multiply that sum by C. Now we can do that because C is k by n, so it is compatible when multiplied to the right of an m by k matrix. So remember, the number of columns of the matrix on the left has to be exactly the same as the number of rows of the matrix on the right. Now, if these were just numbers, then you would say, oh, that's just A times C plus B times C. And you would be correct. But as we're going to see later, the order is very important. So the correct right side for the property home, the distributive property, is we will get the same answer with A times C plus B times C. So again, these products are compatible because A is m by k and C is m by k. So that product is defined. And how big is it? It is m by n. So both of these matrices, B times C, will also be m by n. And so we can add them together, and that will produce another m by n matrix. Since the left side is also an m by k multiplied by k by n, the left side is also m by n. Both sides are m by n, but we will also show not only are they the same size, they contain exactly the same entries. Now, you can also reverse this and this time add two matrices C and D, which are both k by n, and then multiply that sum on the left by A. And this time we will get A times C plus A times B. Now, finally, we can incorporate matrix multiplication with scalar multiplication. We can multiply B times C first, and then multiply that matrix by R. It's exactly the same as multiplying B by R first, and then multiplying that answer by C. Or you can multiply C by R first, and then multiply that answer by B. All of these products should be exactly. All right, let's prove the left distributive property. We have A plus B first, and then multiplied by C on the right. And on the other hand, we can multiply A by C and B by C. Add them together, you should get the same answer. So what's the idea here? We will partition C and D into their columns. So in our last video, we saw that that is one way by which you can define matrix multiplication. Partition the matrix on the right into columns, and so when you multiply by a matrix on the left, we know exactly what's going to happen to them. So we add them together first, and when we do that, we just add the pairs of columns together. So in column 1, we will get C1 plus D1, and so on. So now, when we multiply by A on the left, we will multiply each of these columns by A on the left. Again, that's the definition of matrix multiplication using the matrix on the right partitioned into columns. So now, we have something here, and it's something that we've seen before in chapter 1, okay, where we saw A times X plus Y. We said that that distributes into A times X plus A times Y, and that property is also known as additivity. So the first column is the same as A times C1 plus A times B1. Same thing with the second column. You can rewrite that as A times C2 plus A times B2, and so on. So now we have this new matrix, but we can separate the terms containing C, C1 to Cn, and put them into one matrix. So this A times C1 will put into column 1 of this matrix. This A times C2 will put into column 2 of this matrix. The D's will go into the second matrix. So we will have A times D1 going into column 1 of the second matrix. A times D2 going into column 2 of the second matrix, and so on. So of course, let's check. If you add these two matrices together, you will get exactly this matrix. We have AC1 added to AD1, that is A times C1 plus D1. But now, what are we looking at here? It's like we multiplied C1, C2 to Cn by A on the left. So the first matrix is just a product A times C. And similarly, this looks like the matrix D separated into columns multiplied by A on the left. So that second matrix is just A times D. Okay, so before we get carried away, let me introduce two of the notable exceptions to properties which are possessed by real numbers and vectors, but which are not possessed by matrices. The first exception is matrix multiplication is not necessarily commutative. Sometimes it is, but most of the time it's not. So let me show you. Let's make a couple of 2 by 2 matrices. We'll just keep it small. And then, so I have to see what we are inputting. So there we go. We have our input boxes. So let's make 2 of these matrices. Okay. So if you just randomly put numbers inside these 2 matrices, 7, 9, and then 4, 1, negative 2, 3. Then what do you get when you multiply them in that order? Okay, you get that matrix. But now, what if you reverse the order? So let me take the matrix on the right, put it on the left, and put the matrix on the left, this time on the right. Will we get exactly the same number? Boom. Of course not. And if you look, not a single entry in those 2 matrices are the same. We get 2 completely different matrices. Now, of course, sometimes the matrix product is commutative. So an easy way to do that is to change one of the matrices. Okay, so let's turn this into 3, 0, 0, 3. That looks a lot like a very famous matrix, don't you think? It's just like 3 times the identity. What do we get? 9 minus 6, 21, 27. So what if we reverse the order? So first matrix, we didn't change it. Now that second matrix, do we get a completely different answer? So this time the 2 matrices are exactly the same. And yes, that should not be surprising because this matrix is simply 3 times the identity matrix. And it's easy to see that if you multiply a matrix by the identity matrix, then you don't change the matrix at all. In fact, why don't we see that right now? If you change the 3's into 1's, what are we going to get? Multiply? It's exactly the same matrix. So of course, that's true in general. If you multiply any matrix by the identity matrix, you will get exactly the same matrix. And it doesn't matter if you reverse the order. As long as the matrix product is defined, the 2 matrices are compatible, yes, you will get exactly the same matrix. Now, while we're at it, what happens if you turn all the entries into zeros? Gosh, I wonder what will happen. Oh, I have no idea. Just kidding. Of course, every entry becomes 0. And of course, we can see that just by the definition. Who will we get in column 1? You multiply the 0 matrix to 3, 7. What does that mean? multiply first column by 3, second column by 7, add them together, zeros added to zeros, they stay zero. Now, the second exception that I want to show you is that there is no such thing as a zero factors theorem for matrix multiplication. What is true for real numbers? If you multiply two real numbers together and you get the answer 0, then one of them had to be the number 0. We just saw the zero matrix, okay? And it has a magical property, I guess, although not very surprising, that if you multiply any matrix by the zero matrix, all the entries also become 0. Of course, let me also mention that the size of the product might not be the same as the size of the original zero matrix. So, what am I getting at here? You can multiply two matrices and get as the answer all zeros, but neither matrix on the left will be all zeros. Okay, in other words, we can make these two matrices so that at least one number in each matrix is not 0. Okay, well, if that is our only standard, well, it's not a very high standard. How about we turn these three entries 0? Okay, and then this entry, that's not 0. Okay, so again, all we have to ascertain here is that at least one number is not 0. The rest can be 0. Okay, so if you don't want that 5, maybe we'll put a 0 here. Okay, and I think we should also have a 0 here, because that will also need to eliminate that 5 when you multiply these two together. Okay, if I put something non-zero here, will it work? Yes, because the 3 here will multiply to the zeros in column 2, and that will disappear. And so we can make this also 0. Is that enough? Let's see. Boom, we get all zeros. Okay, so can we make this a little less trivial? Okay, so can we make this not 0 either? We'll put a 9 there. And how about here? Can we make a 4 there? Will that still be 0? Let's see. Oh, no, not anymore. Okay, so let's just keep that as 0. And how about now? Oh, okay, still 0. Okay, so excellent. We can have two entries here which are not 0, and keep that one entry there as non-zero. Now, I believe in your homework, you're going to be challenged to make an example where none of the entries is 0. Have fun. While we're at it, I mentioned that if you reverse the order of multiplication, you might get a different answer. Okay, so what about now? If we put the 3, 9 on the left and the one with the 5 on the right, will we still get all zeros? Oops, no, we get a 15 over here from the 3 times 5. So again, matrix multiplication is not commutative in general. Sometimes you'll get the same answer if you reverse the product, but if you don't know anything about the two matrices, don't you dare reverse the order of the multiplication. However, there is a property of matrix multiplication which is a little bit surprising given the weird way by which we defined matrix multiplication. Take the matrix on the right, partition into columns, and then multiply each of those columns with the matrix on the left. And how do you do that? Back in chapter 1, we said, now you have to think of it in terms of linear combinations. So for each column, think of the matrix on the left as divided into columns themselves, and then you make a linear combination of those columns, which appear on the left, using the entries on the columns on the right. And that linear combination is what will appear in column 1 of the product. Okay, that's just like a gazillion steps. I'm kidding. So, despite that strange definition, it turns out that matrix multiplication is still associative. So here we go. Suppose that A is an n by p matrix, B is a p by q matrix, and C is a q by n matrix. Then what do we have here? A multiplied by the matrix product B times C is exactly the same as if you would multiply A and B together first in that order. Then multiply that answer by C. So speaking of order, check it out. A, B, C on the left, still A, B, C on the right. So when you apply the associative property, be sure that the symbols stay in the same order. Whatever appears on the left should also appear on the right in that same order. So you should not write B times A times C on the right. That would be so wrong. Okay, so why are these two ways to multiply these three matrices together exactly the same? Let's start off with the size. Are they really the same size? Well, on the left we have B times C. B is P by Q, so that's how big B is. And then C is Q by N. So are they compatible? Yes, because the number of columns in B is the same as the number of rows in C. So the answer is a well-defined matrix, and it is P by N. Now we will multiply by A. So A is M by P, and then B times C, we said, is P by N. So, is that product compatible? Yes, again. Columns match number of rows. And the answer is M by N. So I will steal this, and that is also M by N. Excellent. Now what about on the right? On the right, we have A times B first. So A is M by P, and then B is P by Q. So, compatible? Yes. P and P. So, the product of A times B is defined, and it is M by Q. So, last step, we will multiply the product A times B, which is M by Q, by C. How big is C? C is Q by N. So, are they compatible? Yes. And the answer is M by N. Oh, that's exactly the same as the matrix on the left. Okay, so now let's get down to actually showing that not only are these two ways to multiply the three matrices going to give the same size matrix, but they should be exactly the same. So we're going to do that in two steps, or you might say two cases. In the first case, we will assume that C is a Q by 1 matrix. Okay, so not Q by N, just one column big, Q by 1. Okay, so now this will become A times BX, and this will be A times B times X. So let's start with the right side of the equation. We have A times B times X. Okay, so the key is to subdivide or partition B into columns. And we said if you do that, then the matrix product A times B is just the columns of B multiplied by A on the left. Okay? So this is again a matrix which is partitioned into columns. Okay? So now the next step is to multiply that product by X. And what did we say? You take the entries of X and you multiply the corresponding column by that entry. So we have column 1, a times b1 multiplied by x1. And then you have column 2, a times b2 multiplied by x2, and so on added together. So we're going to show that the left side of this equation is also going to be the same. So let me copy this, and then we will bring it over to the next screen. Okay, so here is what we ended up with in the previous screen. And now we will compute the left side of the equation. We have b times x first, then multiplied by a. So, again, b has been partitioned into columns. Now we multiply 2x, same definition, multiply column 1 by x1, column 2 to x2, and so on. Then add all of them together. So now, what happens if you multiply bx by a? So we will take this answer, and then we will multiply by a on the left. We're back in chapter 1. So we have the distributive property, which I just mentioned a few minutes ago. We can distribute a to each of these terms. Each of these terms is a vector. So we have a times x1 b1 plus a times x2 b2, and so on. That's all the way back from chapter 1. But we also have the homogeneity property in chapter 1. We can take out the x1 in the first term and then multiply it by a times b1. Similarly, we can take x2 out of the second term, multiply a by b2. Add it all together. Is that exactly the same as what we got on the right side? Of course. So now let's generalize. Suppose that C now has as many columns as you want it to have. It's a Q by N matrix. So C will have N columns. Let's call them column 1, column 2, column N. So of course, each of these columns has Q entries. Okay? So now, if you multiply C by A times B, multiplied together, as a single matrix, it will be the same as multiplying each column of C by A times B multiplied together. Okay, but now we're back to case 1. We said that this, where you think of C1 as the x, is exactly the same as multiply B by C1 first, then multiply by A. Okay, so for each column I, quantity A times B times column I is the same as B times column I first, then multiplied on the left by A. So we can rewrite each of these products, starting with the first one. That's the same as A times quantity BC1. And that's A times quantity BC2, and so on. Okay, but look at that. We have A on the left side for each of these columns. So again, we appeal to the definition of a matrix product. We can take A outside of the matrix, and it's like we are multiplying a matrix where the columns are BC1, BC2, and so on. Okay, now wait a minute. That is also in the form of a matrix product. You have the columns of C, each of which is multiplied by B on the left. So this matrix is exactly the same as the product, B times C. Oh, there you go. You have A multiplied by the quantity B times C on the right. On the left, you have A times B first multiplied by the matrix C. That's the associative property. Okay, well, I want to demonstrate the associative property to you. Why not? We have a computer to do it. So we have these three matrices. A is 3 by 2, B is 2 by 4, and C is 4 by 3. Okay, so our goal is to compare the two products. the two ways to multiply those three matrices together and show that they're exactly the same. So we have A is 3 by 2, 3 by 2, and we have B is 2 by 4, and C is 4 by 3. Okay, so let's review what we did in the proof. Okay, let's just make sure that both of these are exactly the same size. What is B times C? Are they compatible? Yes, because 4 is the same as 4. So B times C is 2 by 3. Now we will multiply a 2 by 3 matrix on the left by a 3 by 2 matrix. Yes, 2 columns on the left, two rows on the right. So you will have as a product a 3 by 3 matrix. Okay, now how about A times B first? 3 by 2 by 2 by 4. Yes, that's compatible. And you will get a 3 by 4 matrix. Can you multiply that to a 4 by 3 matrix? Yes, because you will have 4 columns and 4 rows on the right. So you will get also a 3 by 3 matrix. So both of these matrix products can be formed. Okay, so let's get down to the nitty-gritty. Let's do B times C first. So here is B, and then we will multiply to C. Okay, and what do we get? So we get that 2 by 3 matrix. Okay, and now we will multiply by A on the left. So we will take this matrix A, and we will multiply by the product we got here on the right. Okay, and we get that 3 by 3 matrix. Oh, good grief, we have really big numbers. And that's no surprise because you're multiplying numbers together and then adding them up. Okay, so that is A times the quantity, B times C. Okay, so now what do? Let's compare to A times B first and then by C. So let's copy all three matrices and so we can scroll down. Okay, so those are our original three matrices. So now we will do A times B first. Here is A, and we will multiply to B. B is over here. Okay, so we get, oh wow, that is a 3 by 4 matrix. So check out that we had an intermediate step here. We got this 2 by 3 matrix. And nowhere in these computations do we see these numbers. We get a completely different intermediate step. Okay, the A times B first is nothing like the B times C first. And why should they be? They're not even the same size. But now, if we multiply this answer by C, will we get exactly the same answer that we have over here? Ta-da! Of course, they're exactly the same 3 by 3 matrix. Now, the associative property of matrix multiplication is exactly what we need to tie up a loose end from the previous section. We saw, or at least we demonstrated, that if you have a composition of two transformations, if T1 is going from Rn to Rk, and then T2 continues from Rk to Rm, then we can form the composition T2 composed with T1, because the output of T1 can become the input of T2. The domain of T2 is exactly the same as the codomain of T1. And we demonstrated that that composition is also a linear transformation. And we formed a matrix for that composition. And we had no idea how it came from the matrices of the individual transformations T1 and T2. But of course, it's not magic, it's math. It is simply the product of the matrix for P2 followed by the matrix for P1. So again, it's easy to remember this. The order doesn't change. P2 is first, followed by P1, matrix of P2 first, multiplied by the matrix of P1. Okay, so we started the proof over here. Let's give these matrices names. So the matrix of P1 is A, and the matrix of P2 is B. Okay, so A is of course K by N, and B is M by K. All right, so we have to show that the matrix of P2 composed P1 is the matrix of P2 first, which is B, followed by the matrix of P1, which is A. So B times A. Is that compatible? Yes, because B is M by K and A is K by N. So the number of columns for P2 is K. It's the same as the number of rows for P1, which is also K. And the product is M by N. So how are we going to show this? Well, first let's start with recalling. How do we use these two individual matrices? How do you compute T1 of V? Multiply V by A for any vector V from the domain of T1, which is Rn. Similarly, if you want T2 of W, you multiply W by B for any W in the domain of T2, which is Rk. So we're going to use that to prove what we want, that the matrix of the composition is simply B times A in that order. But thank goodness we can appeal to the uniqueness property of the matrix of a transformation. What do we have to show? No matter which V we input into the composition, P to compose T1, it should be exactly the same as what you would get if you multiplied V by the matrix that we want, which is B times A. Okay, so let's slowly unwind the left side of this equation. We have P to compose T1 evaluated at V. The definition says, plug in V into P1, compute T1 of V. Plug that into P2. Okay, but how do we compute T1 of V? We said, oh, it's just A times V. So it's the same as T2 evaluated at A times V. So this is now some vector from Rk, the domain of T2. Okay, so that's like a W. Okay, so therefore, to compute T2 of this W, it's the same as multiplying that W by the matrix for T2, which we said is D. Okay, but now, these three are matrices. Okay, so remember that we think of V as a column matrix. So, by the associativity property of matrix multiplication, we can rewrite this as B times A first, followed by V. That's exactly what we wanted to show on the right. And again, the order does not change. We have BAV and we have BAV. So that is how to get the matrix of a composition. Just multiply the two individual matrices together in the same order. All right, so we're going to end this video with something fun. We're going to compute the powers of a matrix. So what does that mean? We know in arithmetic that x squared is simply x times x. So we can define a matrix product a squared if possible. So we're going to multiply a by itself. But remember, there are compatibility issues. Even a might not be compatible with itself. So if a were 2 by 3, and then you multiply by a, so you have 2 by 3 multiplied by 2 by 3. Oh, but wait a minute. The number of columns is 3 on the left. The number of rows is 2 on the right. That's not compatible. So what has to happen? if you have an m by n matrix and you want it to be compatible with itself, then the number of columns must be the same as the number of rows. Oh, that's what we call a square matrix. Okay, so analogously, a composition of two transformations can be formed if and only if the domain and codomain of that transformation are exactly the same space. In other words, it is an operator. Okay, so let's compute powers. Here's a matrix A. Let's compute A squared. So it's the same as multiplying A to itself. What do we get? We have that answer. Okay, so that is A squared. What's the next power? A cubed. Well, how do we think of A cubed? We already have A squared, so we can think of A cubed as A squared times another copy of A. Okay, so we have A squared over here, and make another copy of A, and then find the answer. Okay, so that is A cubed. And of course, we can keep going. We can compute a fourth power and so on. But before we get carried away, isn't there another way to think of A cubed? Can't we also think of A cubed as A first multiplied by A squared? Let's reverse the order. Now wait a minute. Just a few minutes ago, I was telling you, you can't just reverse the order of a matrix product and expect to get the same answer. Okay. Except these are not completely random matrices. Okay. In that example that I showed you, I just filled in the matrix, each matrix with whatever number came to my head or my fingers. Okay. These matrices are not random. They all came from A. Okay. So should we get exactly the same answer if we reverse the order? It would be the same as taking A and then multiplying to A squared, which is A times A. Oh, but wait a minute. We have the associative property. So it's like ABC, except it's AAA. So associativity says it will be the same as AA times A, which is A squared A. Of course, we might as well show that we will get exactly the same answer. So here's our A, and the A squared is over here. So reverse the order, and do we get the same answer? Yes, of course. Okay, so you can compute A cubed in two different ways. Let's do one more power. What about A to the fourth power? Ooh, so now there are lots of ways to make A to the fourth. I can think of at least 3 ways. We can take A cubed and then multiply by another copy of A. So here is A cubed and multiply by 8. Okay, now what's another way to do it? So just like how we did for A cubed, we can also reverse those two factors. So we can take A cubed and this time put it on the right. So here is the A and here is the A cubed. Do we get exactly the same answer? Of course. It's magic. There is one more way. Isn't there a different one? What's another way to make A to the fourth power? Well, we had A squared over here, didn't we? So we can think of A to the fourth as A squared times A squared. So again, all of these should come up to exactly the same answer. So this time, we will start with A squared and then multiply to itself. a squared times a squared. So notice this is very different now from what we have here. So, do we get exactly the same answer? Yes, we do. Okay, I want to do something else with this example before we move on. Think of it as a bonus example within this example. We computed a cube. We said just multiply these a squared answer with a, and we will get a cube. Okay, and I said you're not supposed to reverse the order, except in this case, it doesn't matter if you do reverse the order, because the associative property says you'll get exactly the same answer. So now what do I want to show? Matrices are extremely sensitive creatures. What would happen if we just change one number here ever so slightly? At 116, for example. Let's make it 117. That's not a squared anymore. So, let's turn that into 117 as well. What is the product in that order? Okay, big scary numbers. Will we still get that same answer if we change the 116 to 117? Let's see. Nope, not quite. Two of the numbers stay the same, but two of them change. 840, 845, 1183, 1176. Matrices are extremely sensitive creatures. Make one little change, and suddenly the property doesn't work. All right, so now that we have a squared, a cubed, a to the fourth, what can we do with them? So we talked about x squared. You can also make x cubed, x to the fourth, and so on. So in algebra, we know about polynomials. So what we can do now is we can think of plugging in a matrix into a polynomial, or in fancier terms, evaluating a polynomial at a matrix instead of a number. So here's a polynomial, p of x, c sub 0 plus c1x plus c2x squared, and so on, up to ckx to the k. And suppose that you have a square matrix, an n by n matrix. We can define the polynomial evaluation, p of a, by the first term, c0, well, there's no x there. Okay? So we're going to turn c0 into a matrix simply by multiplying it by the n by n identity matrix, the same size identity matrix as the matrix A. Now the rest of the terms are easy. c1x turn into c1 times a. Turn x to a. Turn x squared into a squared multiplied by c2. Do all of that, add them together, you get an n by n matrix. That is our P of A. So now that we have our powers, let's compute P of A, where P of x is this polynomial, and A is the matrix in our previous example. So I have copied our computations down below. So here is the original matrix A. We found a squared. We found a cubed. Okay. So we want to compute P of A. So the only tricky part is remembering what to do with that 4. Okay. So that 4, you have to multiply to the 2 by 2 identity matrix. So I'm going to copy it, and I will turn it into the identity matrix. Okay, so that's for the 4. Now we have minus 5x. So we want minus 5 times 8, which is over. Okay, minus 3x squared. We have a squared, which is over here. And then 7x cubed, last term. 7x cubed is over here. Okay, so granted that we have these big numbers, but we know how to perform each of these steps, right? You'll just get 4004. The minus 5 turns this into 20, minus 25, minus 35, plus 45, and so on. Okay? So if you don't have a graphing calculator, you still have an ordinary calculator. You can perform the scalar multiplications first, and then add all of those 4 matrices together. But we have a computer. So what do we get? We get that big matrix. Okay? So that is our PFA. Okay, and that is our video for today. So thank you very much for watching. And as always, you will find me on Facebook, and you will find A Portrait of Linear Algebra, 4th edition, on Facebook, as well as at kendallhunt.com. So until our next video, please enjoy the rest of your day.